Hi. So my name is Enzo Alda. This is work that I have been doing with my research assistant, Daniel Andres Pinto Alvarado. And let me go first. My hook here is, and the reason what I'm passionate about this project is that I believe that computing education is a joke the way we're doing it, but there is hope. Since I'm going to use computing in the title, I want to do a brief history of computing. Okay, and I'm not going to start with prehistoric and the notes and the putting marks on the sticks, but this clay called the Plimpton 322, which you can find on Wikipedia, and this actually is considered by Feline Hermans, who is the world expert in spreadsheets. She did the PhD on it. This is the oldest spreadsheet in the world. This spreadsheet actually contains only values, so it's basically a table of numbers. The numbers are in cuneiform form notation, which of course I cannot read. What's amazing, this table was done around 1800 before Christ. Okay, and the table is a table of Pythagorean triples. All right. Many people have been doing research on this, comparing other tables, etc., trying to figure out, was this some theoretical or just, they're basically a practical table for people, to predict how to, what would be the hypotenuse of a rectangle with certain sides, or rectangular, rectangular triangle, I mean, not a rectangle. So there's a lot we don't know about it, but we know that there are Pythagorean triples and there are errors. So like every spreadsheet, it has errors. So this is computing because they clearly computed this. Okay, there's evidence of computing here, even if it was just entirely empirical and not with like a theorem proofs, etc. Like the Greeks, over 1300 years later. This predates the Greeks by a lot. The Greeks use deductive reasoning, and that's important. The Greeks use logic. They began what will eventually become the computing science and the ways that we do today with rigorous disciplines. Okay, I mix the colors to see the blue is the practical, is the software engineering, is the just calculator using a pocket calculator, stuff like that. And the gold is, the science, trying to do theorems, trying to derive results. Skipping very quickly about the Romans, they're dear to me. The Indians did incredible contributions. The Roman contributed a horrible numeral system, right? But they were good engineers. In fact, I was surprised. I was last year here in Coimbra. I didn't know there was a Roman aqueduct there. In Portugal. That's quite far. Okay. Computing or math, if you want. Okay. Math really took off with the scientific revolution. There were certainly some developments during the Middle Ages, etc. Not to negate that, but it's really, this is the golden era. Began with Leibniz, Newton, Pascal, blah, 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 blah. 17th, 18th century, 19th century, started getting interested after Gauss. These last four are interesting. And it's a coincidence that are in black and white. I took this from Wikipedia. This is Cantor, Alfred and Whitehead, Hilbert, and Bertrand Russell. Because these people started to question, like how we could make these regulars. Let's lay the foundations of the mathematics. And indeed, the 20th century was a century called, this is when people start dealing with the mathematics foundational crisis. And Hilbert comes with his program. He said, we need to formulate things precisely, okay? All mathematics should be written in a formal language and manipulated according to well-defined rules. Do this by the book. Completeness, a proof that all true statements can be proved in the formulas, right? Consistency, they definitely want consistency. If you have a system that is not consistent, anything can be proven true. So consistent is it's a deal breaker not having consistency. Conservation, I'm going to skip that one. Decidability. There should be an algorithm for deciding the truth or falsity of any mathematical step. Now, this is a very ambitious program. She thought feasible, it was feasible. And in a way, it would be a great form of artificial intelligence, because if this is true and there is an algorithm, then a machine would be able to do the algorithm, and then we can just use the machine and give it a formula like the Fermat theorem there that it took, I don't know how many years, centuries, to prove, and give it to the machine, and the machine algorithm will prove it. Let's say true is true or is false. And here come the negative result. Kurt Gödel, born in 1906, I believe, comes with incompleteness theorems. Theorems plural, there's more than one. This one in particular is important for my talk to some extent. Any system based on a computable set of axioms and capable of expressing the arithmetic cannot be complete and cannot prove its own consistency. So completeness, a proof that all true statements can be proven in the formalism. Hilbert believed that it was supposed to say that you have the formalism, and any statement in the formalism that is true, you should be able to derive from the axioms. No, you cannot count on having completeness. Something like the arithmetic, look at addition, subtraction, multiplication, and greatest common divisor, everything that you can be with the arithmetic just within just not complete. Not complete. And the decidability, well, definitely no decidability. And about the consistency, a proof that no contradiction can be obtained in the formalism. The decidability, I know they cannot be attained because there's a relationship between this. And another negative results that will come in the next slide, that comes at the hands of Alan Turing. You cannot have an algorithm that decides if a program will halt or not. The halting problem. It has a funny name in German. The 20th century, I call it the first half particular. That was like a shock in the sense, like we hit a lot of negative results. Hilbert program, no can do. In physics, Heisenberg, well, not in disability, so like a, what do you call it? Basically the indeterminate, you cannot determine the position of an electron and its momentum at the same altogether. If you either get one or the other, if you get one, the measurement of the other, you cannot tell exactly, okay? So that was a negative result in the realm of physics. And the other one I mentioned, the other one came computing science that was born here. Because of that crisis in mathematics, people started experimenting with, okay, let's simplify things. Let's take something very simple and see what the properties are, what we can do. Because at the bottom line, what basically Hilbert was saying, precise formulation, and everything should be manipulated according to rules. It's called a rewriting system. Hilbert was clear about this. Is we're just putting things there, writing precisely, and we are rewriting and rewriting. So by this process of transformation of the formula, etc., we should be able to derive like a true or false. And well, Alan Church worked on this. He invented lambda calculus. Or some would even say he discovered, because it's kind of like so simple and so basic, like we think that aliens in other parts of the universe will find this also. We'll write it differently, but we'll come to the same. It's only basically three productions here. Symbol, abstraction, that's the functional abstraction, like a function that takes a number and adds one to the number first, and the application. Like that function that I mentioned before, you apply to the number 4, and that gives you 5. So functional abstraction, functional application, the operation. I give an example. When you apply the function that says give me the successor of 4, gives you the 5. That's called beta reduction. It's a rewriting. And as you know, you do programming. It's basically what you call a function, and the parameters get substituted by the value of the arguments that you pass to the code. And the other is the alpha conversion called alpha reduction. It's just doing rename. And that is to avoid collisions in the statements, because the rules of scoping rules, etc. So this is so simple, and it's incredible, because this is what we now call Turing complete. So with this, you can do arithmetic. In this, he encodes numbers. In this, he encodes all sorts of functions. He can compute greater GCDs, greater common divisor, etc., etc. You can do arithmetic with this, which by Gödel's theorem, that means that this system is not decidable. It's not complete. Meanwhile, Turing did his own formalism that was actually something more. So it's like a Turing machine, okay? And there are actually approximation of Turing machine. You cannot build a Turing machine 100% because it has to have an infinite tape, okay? But this is something that sounds more like engineering style. This is a machine that reads ones and zeros on a tape, and it can change the ones and zeros. It basically is similar to what the computers do, that they read from memory and they alter the memories. It's kind of like a bit imperative. And to their surprise, it was Alan Church, I believe, proved. Alan Church, he studied lambda calculus and realized that he could emulate a Turing machine. And they proved this vice versa. And they basically proved, holy smokes, these two things are so different, and they have the same computing power. And from them, they come to the Church-Turing thesis, which is not a theorem, but at the same time, it's something like, I won't go into why, it's kind of something that can be proved. Okay, so that this is what computability is, the limit. So any formal system that does computing, this is the most power that can have. This is the limit of computability. Well, if lambda calculus is actually the predecessor of functional, it's a form of functional programming, not a predecessor. Lambda calculus is a functional programming language. The Turing machine is a clunky. Some have made steampunk versions of it. It's similar to von Neumann, architecture. And von Neumann is a very smart mathematician and very theoretical himself. He's also an engineer. He worked in the Manhattan Project, and he started building computers with vacuum tubes, etc., trying to help verify calculations for the atomic bomb. And nobody got it. Those machines lasted a few minutes, and then they were the views of ceasing, and Oppenheimer was complaining, and yada yada. So, but it was the atomic bomb was done by human calculators, and the calculators at that time were human, but they used the von Neumann a little bit to verify. And so, meanwhile, there came the machines in the 20th century, but let's give credit that Babbage actually came close. He built, he planned, he designed a different engine, and it will have worked. And we have proved that will have worked because we actually built 2 already that I know of. One is in California and the other one is in London. And he had actually the vision of something that was like modern computing, the analytical engine, something that could do with programmable in the ways that we do advanced programming and everything. But the 50s gave us ENIAC. There was something that the Z3, the Konrad Zuse in Germany, impressive what he did, was destroyed by the bombing. I think we found later that actually this computer existed. There's something that Atanasov or something like that built up. But the truth is that the first truly programmable, general purpose electronic computer was ENIAC. And ENIAC, again, military, ENIAC worked on the hydrogen bomb, the calculation, etc. And the other computer of the 50s, and the only other one that I know of, is the UNIVAC, okay? Which play a role in my life, but that's not very important. UNIVAC is very run UNIVAC. There come the 60s, and we start already working on supercomputers. CDC, that was doing parallel computing, etc. And Craig, who worked at CDC, started his own company, and they came the mini computers, the DEC and Digital Equipment Corporation. You know this. Eventually, this is the machines that will give birth to units. And this glorious 60s gave us a lot more, and so because it was the decade of the moonshot, the Apollo program. And some people don't know, even those who know, underestimate the importance that the Apollo program had in the development of computing. Okay, among other things, it was this invention, the transistor, that was from the 50s, I believe. But for the first time, they were used at scale. They put it in integrated circuits. This here that I'm pointing, I don't know if you see the point, right to the bottom is the Apollo guidance computer. The Apollo guidance computer, the hardware itself was amazing, and I forgot the name of the person that built it, precisely to have certain characteristics of resiliency versus not being able to handle a lot. But this, I call her, she's so young here. This young woman, Margaret Hamilton, Medal of Freedom, given by Barack Obama, don't know in what year, but she was the lead. She started on the position. She raised to the rank. She became the lead of the software engineering team, the people writing the code. And this is the code that will enable men to land on the moon. And it was critical. And this had to be thoroughly tested. The term software engineering did not exist. She used it first when she said, this version of the product, let's separate the like the testing of the hardware, the thing, and the testing of the software. So they separate the hardware engineering and the software engineering. And people sometimes made fun of that she invented this software engineering. They thought software is not engineering. And guess what? One of the hardware engineers said, no, what you're doing, guys, is engineering. And so software engineering was born as a term. Okay? And on that glorious July 20th, when the Eagle was descending on the moon, and 5 minutes before the landing, the 1202 alarm started sounding because the AGC was flooded with too many communication. The story is long, and you can find it in Wikipedia. It's a bit more complicated than just the radar was on and was sending more messages, etc. It was a little bit of panic, okay, when I also say 1202 alarm, and quickly, what's happening? Do we abort, etc. And about 20 seconds later came the answer, but just while Armstrong was saying, do we have a reading on that alarm? The answer was already coming from an engineer called Jack Gorman. He had memorized all the error codes and knowing what to do quickly. And that was because Gene Kranz, still alive, asked him to do that. That's how close we came to not land on the moon that day, okay? But the reason that we were still going that alarm was the code that the team and Margaret Hamilton wrote that was able to discard the messages that were not critical and prioritize the ones that were critical. It's very complicated to program those kind of systems. Asynchronous, concurrent, and have to do many things at the same time and have to be resilient and handle in near real time. The 60s also gave us the mother of all demos. Doug Engelbart, which many people don't know, he basically kind of the founder of human-computer interaction. He is the one that first realized the computers are a way for us to augment the human intellect. And he coined the Engelbart law. He said the intrinsic rate of human performance is exponential because we use the technology, and the technology itself helps us improve on the improvements. That's a bootstrapping, getting better, etc. And we do that all the time. The history which I live is computer science is like we started with machine code and with flipping switches and then entering them in the computer. Then we put assembly language, and that was already, wow, much better symbolic. And then we start writing high-level language. Fortran was a titanic effort. Took 6 people, 3 years, 18 main years to build the first language to be able to, you just write a formula very similar to the way you write it in an Excel spreadsheet and have it compiled to the machine where it can run. 18 main years of effort, okay? But the bootstrapping, the productivity, yes, grows exponential. And will that keep going all the time? I have some considerations at the end of that. But Engelbart clearly very influential in this regard, and he invented the mouse and a bit of other things. Then come the glorious 70s, okay? By the way, I was not just alive, I was sentient when the Apollo landing happened, etc. I started being, my oldest recollection is from 1967, casually, and that was when in the news came that the Apollo 1 astronauts had died in the fire. That made an impression on me as a child, and that's my oldest recollection. Then I followed the entire Apollo program. This is what I'm what do you call? I'm fanatic about this. But the 70s was the Cambrian explosion of computing. Because until now, really, people, common people, didn't tend to have computers. And I'm not going to say that in the 60s, everybody started having computers. No, actually, it was a minority of people, but computing for the first time went mainstream. That some people conceivably could buy a computer. I believe the Apple II was something like $2,000. And the Apple deserves to be at the center, because the Apple was at the center of this revolution. There was also the Tandy Radio Shack, and then the others came in the early 80s. Epson QX10, some Ataris, the Amigas, the IBM PC, which changed the world in its own way. But the 70s, we started first with the computing, the calculators, and HP in particular. And I had this one, the HP 21, was my first calculator, and helped me understand Polish notation, reverse. And 2 years later, I bought the HP 67. This machine, by the way, is a mini computer. It's the PDP 1170, which is kind of important for the Unix. Well, that calculator, and I learned to program it, and I showed it to my statistics professor at the University of Naples, where I was studying sociology and statistics. I will eventually major with sociology and statistics. I showed it to my statistics professor. I have programmed the test for the difference of the means of two populations in the T test for the means of two populations. I understand now, because there were not many people at the time that would do kind of this stuff, and much less in a discipline like sociology. He grabbed me by the arm, like almost like he took me from the ear. And this is the university I was in on the right. It's kind of a big building. Actually, there were many buildings. The University of Naples has many buildings, but this is probably the biggest one. And so it was around here. And there is this, this is the main road that takes to the train station. This is called Mezzocanone. He took me up this road, Mezzocanone, up here, and where the green light said, that is the center of, or was, there's no longer there, the center of numerical calculus at the University of Naples. And he told me, you have to learn Fortran on your own. You're doing research, you will be my research assistant. I couldn't believe my ears. And so at age 19, I started programming. It was a blessing. And for over 3 years, I programmed in Fortran. In those years, in 1979, appears VisiCalc, okay? And the Apple had appeared, I believe, the year before. VisiCalc was an explosion within the Cambrian explosion, because business started buying Apples like hotcakes. This was really what made personal computing popular. VisiCalc. Spreadsheets are the reason people were buying computers. Most people buying computers because they wanted to run VisiCalc. They were paying over $2,000 to run a software that costed a lot less than that. The plaque, and I'm in Boston, coincidentally. I don't know, my life keeps bringing me all these coincidences, that in 2021, I ended up moving to Boston. And I see the plaque in Boston. First widely popular application, 1979, invented by Dan Brickley. Life gave me surprises, and although I had found a job in Italy, I had to go back to Venezuela. Because my parents had moved there. But it was not entirely bad, because the university in Venezuela at the time had very good professor, was very well funded. This was the years of prosperity with YOL, etc. in Venezuela. And I studied computer science, did my master. By the way, after the first 4 years, I became already a professor, and I was teaching while doing my master. And I was passionate about programming language design and implementation, and I am to this day, okay? Particularly compiler construction. And this is a classmate of mine who is a genius. We're both kind of studying at the same time. And he actually, we gave a compiler construction course in 1988. And then in 1989, he said, let's not repeat the same, which was a success, resounding success, the exercise, the language that we had asked to make the compiler, and most students were able to complete the compiler, which was usually not the case, because we changed the way we were teaching it. He decided, because he's the kind of person to shake that, and he created a language that was very strange. And I couldn't understand the language. That didn't make sense to me, because it was nothing like the Fortran, Pascal, C, the language I was used to. It was like a different paradigm, although I didn't know the word at the time. And after 2 days of anguish, I realized it says, oh, this behaves like a spreadsheet. And that is the reason I'm here today presenting. Because that puts that bug in my head. Because if this language replicates or mimics what a spreadsheet does, means that spreadsheets, in a way, are the programming language. They are a computing environment. But it was a crippled one, I already realized in many ways. The language he created was called Lily. I'm going to jump I moved to America in 1992. I started working on this project a little bit, but not much. I was working, okay, I worked at Bloomberg, I worked at Google, and in 2010, I realized I'm getting old. I'm never gonna realize my dream. I almost went bankrupt in 2002 after my MBA, because I tried to start a startup, and the internet, the year 2000, you know what happened. The internet bubble burst. So I almost went bankrupt in 2002. I worked at Bloomberg, I went at Google, and in 2010, I did not have a retirement, but I had to say, I have a retirement in Italy or in Latin America, cheaper places. So I decided to quit. And I am here to this day. In 2015, thank you, Dennis Mankel, and thank you, oh my God, I forgot the name of the one that he passed away, because they were the first one that gave me the opportunity to present my research. So the ZenShip project, it's took a language-centric approach. It's very important for me to realize, if it's a language, you should have a language. Language should mimic spreadsheet semantic. And the interface, the UI, should be independent from the computing engine, okay? Form for solution to the view should be a manifestation of the model. And I was not clear how this would be realized, okay? But it was good I had this intuition, because I knew already spreadsheet is a problem, that the model and the visualization of the model are entangled, because those worksheets, that's where you put your formula, that's your memory for the program. It's also your UI. And then when you wanna rearrange things, etc., you easily can break the formula. But there are other reasons I don't want to go into why that entanglement is bad, and it's notoriously bad in software engineering. Model and view should be separated. The view should be a rendering of the model. How should we define variables that behave like cells? Can worksheet be unified with arrays, indexation, and a one notation? And is it possible static typing and dynamic typing to coexist? These were questions I had back then. I did not have the answers, okay? This in particular, why I wanted to unify worksheets with arrays, because I wanted a language that will work for doing number crunching. I started with numerical number crunching in Fortran. Number crunching is something that people do a lot with. I wanted spreadsheets to be efficient, and indexation is what gives you efficiency. But I wanted something that spreadsheet practitioners will be able to use it, because I had already this vision, the wide spectrum computing, something that people who don't know how to program can still program in that, because people who use spreadsheets are already programmers. They just don't know it. Okay? Okay, so I'm gonna have to define the spreadsheet core. Otherwise, some things don't make sense. Spreadsheet core is what VisiCalc was at the very beginning with only one change. VisiCalc had only one worksheet. No, there's no reason why not to have many, like Lotus did. And let's stop there. Worksheets are all you need to do Turing completing, to code Turing complete and to work well. You enter your formula there, and having multiple worksheets is like having multiple memory banks. That's it, okay? Now, spreadsheets were soon contaminated, so to speak, but for a reason, with extraneous stuff. Like, you don't want to build a software in the spreadsheet itself. In fact, it would be impossible to build it. So add-ins, plugins, etc. But more importantly, you cannot mutate anything because the spreadsheet is purely functional. It's just a set of equations. So when you wanted to automate, like let's add another quarter to my accounting, etc., you want to automate that, but you can't. You couldn't. And then they start inventing the macros, but the macros don't generalize well, are a pure abstraction. And Microsoft versus okay, let's buy the bullet. We need a real programming language. And so plop, they plop Visual Basic on top. It's a horrible decision. It creates a lot of like impedance, etc. And this is the reason, one of the reasons I wanted to do this. I say there is no reason why we cannot generalize spreadsheets and give it also effectful computations. And here is the secret sauce. How does this work? 40 minutes, I still have the time. If you have programming in C, Fortran, or other language, most languages, imperial language, you have assignment statements. I'm representing the assignment with colon equal, like Pascal notation, because in spreadsheets, I don't want to use the equal, because the equal means equality. And I'm not going to change the equal for equal equals like Kernighan and Ritchie did. Nothing wrong with that, because people who use spreadsheets and say, what is the equal equal? So equal for me is equality, and this is the assignment. You assign the number, you assign 4 to x. X is denotes a location in memory, and it gets the number 4. So that is the state of the variable. This assignment, well, the right-hand side has a formula, has an expression, yes, but the semantics is you evaluate, very important word, the right-hand side of the assignment, and the result of such evaluation becomes the content of the variable. And the content of the variable is also the value of the variable in all those languages. So if you ask, this the greatest thing is the prompt. If you ask, oh, tell me what's y? It tells you y is 16. It's correct. I computed 2 times 4 plus 8 is 16. What happens if I increase x? And I do this to my students. I teach remotely, okay? With the ones that have not done programs. So what do you think would be the y? And some people say 15. And some people say, some people say 16 and some people say 18. Why? Because some people have not done programming, have done only mathematics, and they see the equal sign. They actually think in equations, more like spreadsheets, and they say, oh, well, if x is incremented, now y changes. not realizing that, wait a moment, say that x equals x plus 1 will be a contradiction in itself. Right? So let's stop there. In C, in other language, y stays 16. The state of y was 16. We did not change the y. We changed the x. Y is not tied to the x in any shape or form. Spreadsheets have different semantic. Because what you put there is the formula. Yes. However, I wanted the language not to force all the variables to be of that type, that they have the formula lazy. Why? Because that inherently makes the language less efficient. And again, I wanted also to be fast, something that approaches the speed of languages like C sharp, at least, or C. So I mean, just to reinforce, I think you already know where I'm going. The spreadsheet semantic, okay? And here's how we do. Same, I put 4 in X, but I put in Y not the result of evaluating the expression 2 times X plus 8. Not the result, but the expression itself. And the way in the language, I signal, keep the expression intact is with the quotation. The quotation actually has a nice semantic. Remember, I said very important, the word evaluation developed. The semantic of the assignment has not changed. The semantic is still the same. The right-hand side, it's evaluated. But notice the right-hand side doesn't say just 2 times X plus 8. It says 2 times X plus 8 in quotation. The semantic of the quotation is that when you evaluate something that has the quotations disappear. And what leaves you is the expression intact. That's a beautiful semantic, okay? Evaluation and quotation as like matter and antimatter. They annihilate each other. And you leave you the formula. And again, so the result of evaluating the right-hand side becomes the content of the variable. And I put it in brown again to say, like this 16 here. That is the real state of the variable. That is the content, the state of the variable. This is what the variable is. Now, when you want to see it, and in the spreadsheet, you see all the time, because you want to see the spreadsheet, you see the result of evaluating the variable. In the context of that environment, taking into account this X. If you change the value of X, what should you get here? You know the answer. Would be 18. When rendering the result of the formula, they will say, I'm 18. This we call the R value. Just like in C, the R value of here of Y is 16 and the R value of Y here is 16 again. We call the one in green, not the one in brown, the R value. The one in brown now we call the C value, the content. Strachey did not have to distinguish, did not have to coin C value, the value of the content, what's in the content, because in the Strachey's model of computation, they are always the same. The content of the variable is the value that the variable has when used in an expression, okay? We have to distinguish the C value in the R value. In formal semantics, operational, Strachey, in a context gamma, gamma maps the symbols to locations in memory. Remember that phenomenon? Maps the symbols or expressions that have an L value. Like Strachey, L value means things that can hold the content, things that are assignable. It's not just symbols. A sub I can be assignable in C because A is an array and the elements are independent. So you can assign to just the third element of A. You write A sub 3 and you assign. So you take in the gamma context, okay? You look at the expression and say, okay, this expression maps to this location sig by memory. Now there is the other mapping, the mapping of the locations to the content of those locations. Okay. And like you already know, well, in Strachey, that content is also the result of evaluating. So that's what above the bar, you have the premises, and below the bar, you have the consequences. So you say, in the context gamma with a storage context sigma, this expression E sub delta evaluates to V. Why? Because V is the content of location sigma, which is the location denoted by that. It's very simple. For us, in the language of Zenshit, which is called Lily, there is an extra step. These first two are the same as in Strachey, but now you evaluate the content. Now, why the content you see this, instead of V, we see closure expression. The content can be a non-reduced expression. Okay. This is supposed to end in 50 minutes of 12:10. Okay, so I don't have much time left. So, well, for that, I have to skip slides because I want to go to the part of the spreadsheet core. We have the evidence. Spreadsheets are suitable for teaching, okay? Because it's a low barrier of entry. Students in middle school know how to use it, etc. But they are not suitable for teaching because they have a low ceiling. They lack modern programming language concept. They lack functional abstraction. You cannot define functions. They're error prone. Those programming with like a B4 times C7, etc. For God's sake, let's give names to the variable so it's more expressive, okay? These are defects: lack of function abstraction, the type system very simple, they entangle the model visualization, and you cannot perform effectful computation. That's what the Zenshits project does. And look at this. This in Zenshit is an array of doubles, but see, in the cells, they are formulae. This is an array, which elements of the array is an arrays. That's why you see this arrays of different sets like a triangle. And inside you have lazy double, which means the cells have not necessarily can have a double, but can also have a formula that evaluates the double. This actually is the same result, but this is an array of lazy array of double, because this is an array which itself is a formula that results in an array. It's completely orthogonal. If you have a type in the system, array, structs, etc., formulae should be able to generate an array or a struct, etc. This exists in Excel. It's called array formulae, but Excel doesn't handle it as elegant as you see here. As it collapses in the UI. Again, the rendering is a function of the model, and it knows when you're editing or when you're just looking. When you're looking at the C value or at the R value. This is a model that does higher order computing, which means it uses formulae that receive formulae, okay? Like the map is a function that receive a function that tells what mapping to do. Like a map could be take all the numbers in an array and multiply them by 2, etc. In Google, you have a map filter reduce is considered the paradigmatic operations of functional pipelines. That's what the model is called, functional pipeline. You have a set of data, you filter by eliminating some, and then reduce by applying an operation like add or more, or some other like compute the mean, etc., etc. Zenshit was still presented in 2017. Okay, well, in 2015 at the ITPC was pretty clunky at the time. The one that you're looking here was presented in a splash in Vancouver. And then we show also in 2020, we show how we have achieved full unification with the spreadsheets. Again, as I mentioned, dynamic arrays and all these beautiful things. Your questions, if you want to ask, I can give a little demo. finally, at age 61, I got my first publication towards wide spectrum spreadsheet computing. Okay. And here are it's me and 7 of my research assistants up to that date. You have the link. People who ask, send me email. I'm gonna send them the slides so they can see. A year later, at the same conference, the Lambda Days in 2021, Simon Peyton-Jones and Andy Gordon here of Microsoft Research keynote Excel Meet Lambda. For the first time, Lambda expressions were added to the spreadsheet core. Okay, you can do functions with VBA, which should be finally in the core as it should be. That was February 18, 2024, and life gives you coincidence. That day, they were presenting, and the day I get the my phone buzzes, and Javier is there, and I said, Javier, I thought that he was looking at me because he had the links to say that I was there with Simon Peyton-Jones at the virtual. No, we have been accepted. And I cried. And later that day, the Perseverance rover landed. And I say, one thing I have done right, because I've made many mistakes. I should have mentioned that. I made a mistake along the way, which is why this took longer. The only thing I've been doing is persevering. That paper shows like the language of expression of Excel, writing to formalize the actions. And then it shows how Lily, and this is Lily, language Lily, covers all the spreadsheet core. That's what the paper is about, showing that this language can do everything that the spreadsheet core can do. And more elegantly, look at the actions. And if you take the type definitions, which are not even necessary, but it's beautiful, there are the only 2 actions, whereas the actions, which is notorious in programming language design implementation, you don't like when you have a lot of effectful actions. Let's say you want a language that has a rich set of expressions, it's very mathematical, and smaller here. And in Zil and in Lily, this is the case. Rich language of expression, just simple definition and assignment, because that assignment can do the copy and paste values, copy and paste formulae, single cell assignment, etc. The sheet was tested on 9 browsers. I cannot say that that's still true today, the random. This I can skip altogether because I don't think the ITPC is really. This is my next paper. We haven't still published, but we have formalized silly semantics, and I show you only these 2. Remember, this is the one this is the evaluation of a variable. Now, this looks like Strachey because this is the semantic of the function formula. There is a function built into the language called formula when you want to get the C value. And that's important. That is what allows you to do copy and paste formulae, because you don't want to copy and paste the result of evaluating the formula. Most of the time, when you want to generalize or extend a model, you want to copy and paste the formula. However, this is not Lily, I should have said. This is Zilli. And Zilli is a lot smaller than Lily. Why? Because of this. Formalizing Lily semantic, it's never easy to formalize a language. It's a titanic labor. So what you do, just like Church and Turing tried to do something very simple to try to understand and formalize things, we did our formalization of like a minimal language, which has spreadsheet-like semantics. It has only integers, functional abstraction, and lazy, because we have that. And here's the functional abstraction is in the expression is the lambda. This is where it shows the types. I have the type integer, the type function, the type lazy t, right? Functions map something of type t to another type t, probably the same. Functional abstraction is lambda. This is function application. This is the if, the condition, the defer, the formula is the one I told you, the special function that takes the C value without evaluating the X. Defer is the quotation. And then I have the less and the minus, because with the less and the minus, basically subtraction and deciding if something is less than something else, I can build the arithmetic. This language is Turing complete. Random is actually for, we'll say for fun, but random helps face the laziness, because when you define a formula that has a stochastic component, random changes value constantly, you see the numbers changing all the time. And these are the two statements I told you before, design and assign. So in closing, I'm just going to skip all this. I didn't go, but this is also formalization that we implement a discrete model of functional reactive computing, because that is the paradigm of the spreadsheets, functional reactive. In honor of the people who coined the term functional reactive, the original definition of functional reactive computing was used the notation semantic and was continuous. We have to be discrete, otherwise has no practical use. Students already know the syntax because they learn algebra, etc. Language, the language of the programming expression, everything in the right-hand side of language is pretty simple. And it's what they have on spreadsheets. Spreadsheets is an ideal environment because you have the immediacy. You can write things and you immediately see the results. You can test, do what-if analysis, and you can do stochastic manipulations, okay? I'm not gonna go into my future of computing AI because I'm out of time. So unless somebody wants to answer, I have opinions about the singularity and artificial intelligence, which probably might make this project obsolete. But my reasoning is that if artificial intelligence makes this obsolete, if we don't teach computer science, it's not the computer, it's not that I want everybody to be a software engineer or programmer. It's computing. It's important to understand the world. It gives you that discipline of thinking in terms of things that can contain other things, that abstraction, that hierarchy, the parsing of expressions, understand notations, etc., etc. So I stop here. Sorry, I tried to do too much, but thank you for your attention. Hello? Do I have people still there, or everybody has a pen on there? No questions at all? Oh my God.